Good afternoon to you viewers and subscribers. Welcome back to my channel and welcome back to another video. So in today's video, I'm going to continue looking at the continuous one-way slab. Um, I'm going to upload the video in the description for those of you who haven't seen it already. So this is going to form part 2 of that video. So I'm going to show you now how I come up with the reinforcement design for our tension, for our compression, and for our crack reinforcement and the reinforcement over the support. So please watch the video until the end, and in the event that you have any questions, please shoot me a comment in the form of a question in the comment section. And I hope you enjoy this video. All right? Thank you. So I'm going to pick up where I left off from part 1 of this video. So I have gone through all the various steps and I've left out the design reinforcement. So I'm going to pick up where the design of the reinforcement, right? So I'm going to leave the part 1 of this video in my description. So for those of you who want to follow the complete calculation design of part 1 or part 2 and part 2, it can be easy for you to follow. Alright, so our design reinforcement, we're going to calculate our area of steel. And the formula, if you have been following from my previous calculate design reinforcement, slab reinforcement videos, you will have come to realize that the formula to calculate the area of steel is going to be the moment divided by phi times Fy, which is the yield stress of steel, times JD, which we term as the lever arm, where phi is equal to 0.9. Right? So for our first trial, we're going to assume that JD is 0.925D. Alright, and the reason we assume that we want to calculate the exact area of steel, right, and we want to know what the actual value of JD is. So we assume JD to be 0.925, right, and when we calculate our area of steel, we calculate A, since the real value for JD is equal to D minus A over 2. And the formula for A is the area of steel times the yield stress of steel times 0.85 times the compressive strength of concrete times the breadth, which is the width of steel. Alright, so let me go into the calculation of the area of steel now. Right, so our moment from our previous video is 13.35 kilonewton meter times 10 to the 6. So let me show you where we get this 13.35 kilonewton meter from, in the event that you have not been following from the first video, right? So this is it here. So our moment, which we calculated last week, was 13.35 kilonewtons meter per meter. All right. So that's where the moment comes from. Right, so our phi, which is 0.9, and our yield stress of steel, which is 41.4 or 414 newton millimeter square, times 0.925 times the depth, which is 132. So when we work out our area of steel, the value is 293.44 millimeter square per meter, right? But we have to calculate the area of steel exactly, right? So if this is to be calculated exactly, we have to calculate A, right, to find JD. We know what D is already, right? We don't know what A is, and that's why we calculate this preliminary area of steel to calculate A. So A, which is the area of steel times the yield stress of steel over 0.85, the stress of concrete times the breadth, which is the width of the slab, right? So our area of steel preliminary, we just calculated to be 293.44 millimeter square per meter times the yield stress of steel, which is 440 Newton per millimeter square, divided by 0.85 times the compressive stress of concrete to be 20 newtons per millimeter square times the breadth, which is the width, times 1,000 millimeter. Right? When we work that out now, we are getting A to be 7.14 millimeter. All right. So now I can proceed in calculating JD. So JD is going to equal to D minus A over 2, right? Which D, which we calculated previously, our effective depth to be 132 millimeter, minus A, which is 7.14 millimeter, divided by 2, and that works out to be 128.43 millimeter. So the exact value for JD is 128.43 millimeter, and now I can proceed to calculate the actual area of steel, the real area of steel that we're going to work with in this design. All right. So our area of steel, again, this is the formula: the moment times 10 to the 6 over phi Fy JD. And I think I've mentioned previously why I use this 10 to the 6 is that we are moving from kilonewtons to newtons, and we are moving from meter to millimeter. So 1,000 millimeter make 1 meter, so that's 10 to the 3, and 1,000 newtons make 1 kilonewtons, that's another 10 to the 3. 10 to the 3 times 10 to the 3, when you're multiplying, you add indices, so 10 to the 3 times 10 to the 3 is 10 to the 6. All right, so we can recalculate the area of steel now, since we have the actual value for our JD. So our moment, which is going to be the same thing, 13.35 kilonewton meter times 10 to the 6 divided by 0.9 times 414 newtons per millimeter square times the 128 millimeter, and the actual area of steel now works out to be 278.97 millimeter square per meter. So therefore the area of steel at each critical section will be 278.97 millimeter square. All right, so since we have that now, and that's the maximum area of steel, because we use the maximum moment at the support to calculate this moment here, right, of 13.35 is what was calculated previously for the moment at the first interior support. Check out that part 1 video and you will see how I get that 13.35, right, kilonewton meter. Right, so I'm going to show you now our rebar table, our moment table. So if you should look at the table now, right, so this is the table here, folks. So this is the table here showing the cross section of the slab. So we have in our first column we have our length, we have our moment, we have our moment coefficient, we have our moment in kilonewtons meter, we have our area of steel required in millimeters square per meter, we have our area of steel minimum, our minimum area of steel in millimeters per meter, we have our chosen steel, and our area of steel provided. All right, so I've already calculated all these moments. So the moment up for the first interior span, which is the length for the first interior span is 3.675 millimeter. We take it back to our support. The length for our second interior support is 3.45 millimeter, and the length for our third interior support, our third interior span is 3.44 meter. All right, so these are all meter: 3.675 meter, 3.45 meter, 3.45 meter. Again, you have to follow what I've done in the previous video. So our moment, our moment is going to be 139 points when we times our W times our length here, which I think I do a little calculation here. So let me show you how I get the first moment here to be 139.10. So it's going to be 10 to the 3, 10.3 kilonewtons per meter square, which is our W, which was calculated from the previous calculation, times our length, which is 3.675 meter, and that works out to be 39.10, right? So 39.10, and we come here again. Let me show you how I get this 133.48. Let me see if I can find it in the but basically yes. So right. So here it is. For our moment over the support, which is going to be 133.48, is going to be 10.3 times 3.625, which works out to be 133.48 for our moment, and then we bring that, and for our moment at this second interior span is going to be 122.59, and here's how I get that 122.59 is 10.3 times 3.45 square, and that works out to be 122.59. all right, okay, so this is our moment here, right? So the moment for the first interior support, the moment for the first interior span is going to be 139.10, right? Our moment for our first interior support is going to be 133.48. Our moment for our second interior span is going to be 122.59. Our moment for our second interior support is going to be the same, 122.59, and our moment for our third and final interior span is going to be 122.59. So if you're listening to me carefully, you would have heard that I mentioned the moment for the first interior span as again the moment for the first interior support. So we are calculating our reinforcement for our span and our reinforcement at the support. Okay, right. So basically, our moment coefficient for the first interior span is going to be 1/14. Our moment for our first interior support is going to be 110. 1 divided by 10 against 1 divided by 11. Our moment coefficient for our second interior span is going to be 1/16, and 1/16 here, and 1/11 here. All right, you can follow what I'm saying here. And then when we work out now for our area steel, right? When we work out the area of steel, so the area of steel here. So I'm going to show you how I get the first area of steel to be 293.4. And of course, the reason why I have 0 here for our first column, the length here is going to be 0. The moment is going to be 0 here too. So over the first NB support, our moment and our length is going to be 0 because there's no length. So there's not going to be any moment. And if you go back to the moment distribution diagram, you would have seen where here the curve started here. So there's not going to be a moment here at the first interior bay, and our last interior bay there's not going to be a moment either. All right. So our moment at the first interior at the first end bay here, this end bay here is going to be 0. Right, because the length is going to be 0. All right, so because we have to calculate the area of steel for this top reinforcement here for cracking, we're going to have to use the minimum reinforcement. Okay, and the minimum reinforcement is going to be 0.0 0.018 times breadth times height, which works out to be 0.018 times 1000 times 163, and that works out to be 293.4 millimeter. All right, so that's the minimum area of steel here for this top bar here. All right, so the area of steel for our tension reinforcement in the first interior span is going to work out to be 207.51, and let me show you where I get that. So the moment is going to be 9.93, which is going to be 1 over 14 times 139.10, and that works out to be 9.93. So it's going to be 9.93 here, right, which is 9.93 times 10 to the 6th over 5, which is 0.9 times yield stress of steel 414 times JD 128.43, which works out to be 207.51. all right, so we come here now at the first interior support. So we're going to calculate the area of steel for this bar here, the over support here. So it's going to be 133.48 times 1 over 10, which works out to be 13.35, and 133.48 times 1 over 11, which works out to be 12.13. And of course, we're going to go with the higher. All right, so when we work out the area of steel for that, the result is going to be 278.97. So it's going to be the area of steel, which is 13.35 times 10 to the 6th divided by 47,853.02. Remember now that comes from 0.9 times 414 times 128.43. That works out to be 47,853.02. When we divide that into 13.35 times 10 to the 6th, the result is 278.97 millimeters square per meter. So that's how we get this 278.97 millimeters square here, right? Then we come now to work out our second moment, which is going to be work out to be 253.48. So we have our 12.3 here, right, times 10 to the 6th divided by 47,853.02, and that works out to be 253.48. all right, now we come here, we do the same thing here, right, which is for the area of steel, which is going to work out to be 7.66 times 10 to the 6th divided by 47,853.02, and the result is 160.07 millimeters square per meter for our area of steel. We come here, we do the same thing here, and get the area of steel to be 232, right, 0.16, right? So here it is. So it's going to be 11.11 times 10 to the 6th divided by 47,853, and the result is 232.16 for area of steel. And of course, the area of steel here for our tension here, right, is going to be the same as the distance here, which is going to be 160.07. So I've shown you how to get the area of steel for our top reinforcement here for cracking, or area of steel for our tension zone here, or over support here, right, and our tension reinforcement here, or over support here, or tension reinforcement here at the bottom of the slab, and our area of steel here for cracking. All right, but watch this now. The minimum area of steel works out to be 293.4. all right, so at no time we can go below the minimum. So if you look at all of these area of steel here, the area of steel here is going to be 207.51, right? And then we have an area of steel here of 278.97 and 253.48 for our over support here, which we go with the higher of 278.97, which is less than 293.4. So basically, we have to go all the way through this reinforcement of this slab with our area of steel of 293.4 millimeters square, because all area of steel is less than 293.4. all right, so we go to our rebar table now, right? And since we are looking for a value closest to 293.47, we're going to look for a value closest to this to come up with the area of steel, right? So if we should go to our rebar table now, right, to look up 293, right, the closest thing to 293 is 312, and 312 millimeter, right, it is a number 10 bar or a 3/8 bar. So pretty much what we have come to realize is that we could basically reinforce this slab with 10 millimeter bars or 3/8 bars, right? Because the closest thing to 293.4 is 312 millimeter, and that can be found beneath the 10 millimeter bars. All right, so this is 10 millimeter here. So it's the 312, and then our spacing is going to be 250 millimeter square. But because I want to be on the conservative side, right, I want to put my reinforcement bar in my tension zone in the bottom fiber of the slab here to be 1/2 inch, right? I just want to be sure. I'm not going to reinforce the tension zone here with 3/8, even though I could. But I'm going to reinforce it with 1/2 inch. So the closest thing for a 1/2 inch bar, according to the rebar table here, is going to be 377 millimeter, right? Which is greater than the which is greater than the 312 here. So we're going to choose number 12 bar, right, for 312 millimeter square per meter. We're going to space them at 300 millimeter per center on centers. All right. So if you look at our table now, so we're going to choose for our top bar here, we're going to choose number 10 at 250 millimeters on center. That's 10 inches. For our bottom bar here, we're going to choose number 12 at 300 millimeter on center. And for our over support here, we're going to choose number 10 at 250 millimeter on center. For our bottom bar here, in the tension zone of the concrete, we're going to choose number 12 at 300 millimeter on center. For our top bar here over the support, we're going to choose number 10 at 250 millimeter on center, right? And for our tension bar here, in the tension zone, we're going to choose number 12 at 300 millimeter on center. And for our top bar here, at the end, we're going to choose number 10 at 250 millimeter. All right. So that is it. I have shown you how I come up with the reinforcement. And of course, our area of steel is going to be 312 here for our end bay, right? Which is 312 here at 250 on center. And our area of steel provided for our tension reinforcement is going to be 377 millimeter at 300 millimeters on center, which is right, 377 or 300 millimeter on center. All right, so these are our area of steel provided, and this is our area of steel required. So the requirement for this slab, right, the requirement for this slab is going to be 3/8 bar. I could have reinforced this slab with only 3/8 bar and it would still be safe. But because I want to be on the conservative side, I reinforced all my tension bar here in the tension zone of the slab. I go with 1/2 inch bar. All right. So I'm going to skip a few steps because some of the steps is not necessarily a requirement per se. So here I'm going to skip this step here. That's calculate the maximum spacing. So you see the maximum spacing works out to be 332 millimeter in center, right? And we are below this, right? So you say, so for the code, check reinforcement for spacing for crack control, ACI section 10.6.4. Limit the maximum spacing of reinforcement adjacent to the tension face of the slab. So S spacing is equal to 95,000 over the yield stress of steel minus minus 2.5 times the compressive stress of concrete, right? But not greater than this 300, the open bracket 250 divided by the yield stress of steel, which works out to be 304 millimeter, right? So we have shown you where we on the conservative side. So the maximum spacing should be 250 millimeter on center, right? The maximum spacing is supposed to be 332 millimeter on center, of which I use 250 millimeter on center. All right, and this is what our section is going to look like. I have shown, right? So we call out this bar here, right? This bar here, and remember, when we're dealing with a one-way slab, the main reinforcement is going to be about the sharp direction. All right, so this bar here, which is going to be in the sharp direction, is going to be number 12 millimeter at 12 inches, 300 millimeter on center, right? Bottom, right? And this is our top bar, which is going to be our distribution bar. It's going to be 10 millimeter, 3/8 inches at 250 millimeter on center for our top distribution bar. And we repeat this over the remaining two slabs. All right, and this is for our top reinforcement here for cracking, right? So we're going to use 10 millimeter, 3/8 at 250 millimeter on center, which is 10 inches for our top mat. All right, and our over support bar here, this bar here, right, is going to be 10 millimeter, 3/8 inches at 250 millimeter on center, which is our top mat at L/3, right? So this is our section through the slab here, right? So basically I've done the call out already, so you can look at this. So for this distance here is going to be L/4, so it's going to be a quarter of this distance here, which is going to be 365 millimeter. You divide that by 4, and that's how I come up with this 919 millimeter. And for our over support is going to be L/3, so we divide this 3600 millimeter by 3, and the result is 1225 millimeter, right? And I do the same thing here, right? L/3 here, L/3 here, right? L/3 here, and this is L/4. So L/3, 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 and L/4. All right, so that concludes the video. So this is part 2 of the video. I know I've gone through this calculation very quick, because I do not want the video to be that long. So I've come to the end. So in the event that you have any questions, just shoot me a question in the comment section. I'll be more than happy to answer your question. All right, thank you.